Last time, when we were discussing series, we saw that it was hard to find its sum, the actual numerical value the infinitely many terms of the series add up to. We were able to do it for a few special series, telescoping series and geometric series, but that's about it. And for the most part, we can't do it. Although determining the sum of a series is difficult, it turns out it is not so hard to merely decide whether a series converges or not, i.e. whether its sum is finite or is infinite or worse. We encountered one simple test to do just that already, the test for divergence, which says a series diverges if its individual terms as a sequence do not converge to zero. But, if you recall, the test for divergence was precisely that, a test for divergence, meaning it is incapable of determining that a series converges. Either it's sure that a series diverges, or it's inconclusive. But now we'll turn to a more robust test that is actually able to decide convergence and divergence. It's called the integral test. So what does the integral test say? Roughly, it states that if you convert an infinite series into an analogous integral, the series converges if the integral converges, and the series diverges if the integral diverges. More precisely, it says that given a series whose terms, a sub n, are determined by a function f that is continuous, positive, and decreasing on the interval from 1 to infinity, then the series and the improper integral of f from 1 to infinity either both converge or both diverge. That is, the series and the integral share the same convergence status. The upshot of this test is that although determining the sum of a series is hard, evaluating an integral is, relatively speaking, easy. However, it's important to note that this does not mean that the sum of a series equals the value of the improper integral. It just says that the convergence, or divergence, of each is linked. But why does the integral test work at all? Admittedly, the test seems fairly intuitive, and it states more or less what we might have guessed if we managed to think of it. But still, intuition is not proof, and ultimately, an improper integral is a different beast than an infinite series. So why do they agree with each other regarding convergence? Let's take a concrete example. Suppose we want to decide whether the harmonic series converges, that is, the series 1 plus a half plus a third, and so on. According to the integral test, we would consider the function 1 over x and integrate it from 1 to infinity. That corresponds to the area of this blue region. Let's say we want to approximate this area using left-oriented Riemann rectangles of width 1. Since these rectangles all have a width 1, their areas are the same as their heights, and their heights are given by the height of the curve 1 over x at the rectangle's leftmost edge. This means our first rectangle has area 1, the next has area 1/2, and then 1/3, and so on. Thus, the total area of the rectangles is the same as the sum of the harmonic series. Now, remember that we already know the true area under the 1 over x curve is infinite, since the integral gives us a natural log which goes to infinity. But if we look at our rectangles, they stick up over the blue region, thus overestimating the blue area. And if the blue area is infinite, any overestimation of it must also be infinite. Okay, but what about convergence? So far, this only shows why a divergent integral leads to a divergent series. But what if the integral converges? Let's consider another series that is similar to the harmonic series. 1 plus 1 over 2 squared, plus 1 over 3 squared, and so on. If we play the same game we just did, and take left-oriented Riemann rectangles for the graph of 1 over x squared, we get, like before, that the total area of the rectangles equals the sum of the series. If you recall, the integral of 1 over x squared from 1 to infinity is finite, equal to 1 in fact, which means the blue area is now finite. But since the rectangles are overestimating the area, we don't know whether the area covered by the rectangles is finite or not. They may overestimate the blue area by a finite amount or an infinite amount. But we can change this overestimation into an underestimation with a slight change in the picture. Instead of taking left-oriented Riemann rectangles, let's make them right-oriented. The rectangles are now pretty clearly underestimating the blue area, and since we already know the blue area is finite, the total area covered by the rectangles must also be finite. You may have noticed that what we've got here is not exactly the same series we started with. In shifting the rectangles to be right-oriented, I simply deleted the first rectangle whose area was 1. But if I add 1 to a finite number, I get another finite number, so indeed, the original series has a finite sum.